Hi, and thanks for joining me in this video about fronts. This is a third in a series of videos about fronts. We're working our way through the definition of fronts. The definition is that a front is an elongated zone of strong temperature gradient, strong static stability, and strong cyclonic vorticity. In this video, we're going to talk about strong stability. One way to measure the stability of the atmosphere is to look at how temperature changes with height. If temperature increases with height, it's stable. If temperature decreases rapidly, it's unstable. And another way we can do that is by looking at the potential temperature and how that changes with height. Here we have a cross-section of the atmosphere. The red lines represent isotherms. We showed this in another video looking at how temperature changes as you go from the south to the north. Of course, the black lines represent the frontal zone, and we talked about how rapidly the temperature crosses or changes across a frontal zone as you go horizontally. In this video, we're going to look at the vertical. We're going to send up a weather balloon through the front. And notice that as the balloon goes up through the front, the temperature really doesn't change all that much. In this example, the temperature looks like it's changing through the front. Actually, it's pretty much constant at about maybe minus 11 degrees Celsius. And that's what you find in fronts. You may see temperature that doesn't really change much with height. In other words, temperature is constant with height. Or temperature actually increases with height, and we call that an inversion. And when inversions occur with fronts, well, of course, we'll call them frontal inversions. So these are very stable layers. As you recall from your basic meteorology class, inversions are layers, of course, where temperature increases with height, and they're very stable. So this is what it would look like on a skew-T log P diagram. Notice that down below the temperature increases with height or decreases with height, and then above the front temperature also decreases with height. Right in between, though, where you have the inversion, you've got either temperature constant or perhaps maybe increasing with height. We'll look at the case that we've been looking at throughout these videos, these series of videos. There's an occluded front that stretches down into a cold front and warm front across South Dakota, Nebraska, and Kansas. The warm front goes across Minnesota and Illinois. And we'll look at these four upper air stations. We'll look at North Platte, Aberdeen, Minneapolis, and then also Green Bay. We're going to look at the soundings and see if we can find the front. And this is North Platte. Remember, the North Platte is behind the cold front. So down near the surface, the winds are out of the north or northwest. That's what you would expect behind a front in the cold air or in the zone. And then as you go up through the atmosphere, notice that the temperature does not really decrease all that much with height. It looks rather stable. It's not an inversion and it's not constant, but it doesn't really decrease rapidly. Down a little bit closer to the surface, notice that there is a rather strong inversion. But this layer or this zone is probably the front. Here's Aberdeen, South Dakota. Remember, once again, this was behind the cold front. And you can see down near the surface, temperature decreases with height and the winds are out of the north. But then you notice that the temperature actually does not decrease very rapidly. It doesn't really increase. It's not an inversion, but it just looks like a much more stable layer where temperature doesn't decrease with height. And then above that, the winds are out of the southwest. So that's your frontal zone, cold frontal zone over Aberdeen. This is Minneapolis or Chanhassen. And you notice that there's a very well-defined temperature inversion with the warm front, very strong. Down below the warm front, the winds are out of the southeast, and then through the front and above the front, the winds are out of the southwest. And then at Green Bay, once again, this is out ahead of the warm front. Notice that this is a very deep layer where you have a very stable atmosphere, and that's the front. And it's a little bit farther ahead of the front, so it's more diffuse, as we kind of alluded to in other videos. And then above that, the winds are out of the southwest. So very well-defined fronts that you can pick out on SKU-T log P diagram. The next thing we're going to look at is the potential temperature. How does potential temperature change with height? Remember, potential temperature is the temperature air would have if it were brought down dry adiabatically to 1,000 millibars. And we said that atmospheres that have potential temperature increasing with height are called statically stable atmospheres. Our atmosphere is typically statically stable with warmer potential temperature values up high and colder ones down low. We're going to look at sounding and look at how static stability or how potential temperature changes with height. So lines of constant potential temperature are also dry adiabats. And that's what I have plotted here. I've got potential temperature theta values for labeled for 4 different dry adiabats, the 280, the 290, 300, and 310. Remember the definition of potential temperature. Take the temperature at that altitude, bring it down to 1,000 millibars. And it's constant in a dry adiabatic process. Potential temperature is constant. So if we calculate the potential temperature values, you can see here on the SKU-T, just following that red line, notice that down low potential temperature increases slowly with height. Then in the frontal inversion, it increased dramatically. It goes from like 290 to 300 very quickly in a very short distance. And then above that, potential temperature still increases with height, but more slowly. So we said that where you see a change in potential temperature with height, that is where the air is stable, statically stable. And it increases dramatically through a front with height. So you have very strong static stability in frontal zones. Horizontally, you can also plot potential temperature. How does that change through a front? Well, let's look at the cross-section again. Here's our cross-section, and these are the isotherms. We're going to look at 700 millibars, and we're going to look at temperatures at 700 millibars, and at each one of these points where an isotherm intersects 700 millibars, we're going to calculate the potential temperature. Notice, of course, that potential temperature, or regular temperature, decreases as you go to the north. We have 0 degrees Celsius in the south. Going north, you end up with minus 20 or even colder in the cold air. So we'll calculate potential temperature using this equation. And these are the values that we got for 700 millibars at these particular temperatures. 0 degrees Celsius at 700 millibars would be 302. There you see minus 10 is 291. And minus 20 degrees Celsius is 280. So if we plot all of these, notice that number one, potential temperature decreases as you go north towards the cold air, but also increases as you go up through the atmosphere. So we had lower values of potential temperature at any given altitude or pressure level and higher values to the south. So there's a slope in potential temperature with lower values to the north and higher values to the south. And this is what the slope looks like in the frontal zone. So this is another way you can identify frontal zones, is by looking for the packing and the slope of potential temperature. In our next video, we're going to look at how vorticity changes in fronts.